Hello. Last class, we were discussing how to use entropy as a tool for assigning probabilities. This is the method of maximum entropy. The basic philosophy behind all of this is, is one in which you want to assign a probability distribution, which incorporates the knowledge that you do have and expresses maximum uncertainty about everything that you do not know. So what this is really is a method of maximum honesty. Take into account what you do know and be very, very honest about the fact that there are things you don't know. So how does that get implemented? Let's go to our tablet. And so basic idea here is going to be you have a discrete variable. The Shannon entropy only really in principle applies to discrete variables. And we want to evaluate or assign probabilities to these various alternatives. So the statement that we want to be maximally honest about the fact that we know very little is implemented by saying you're going to maximize the entropy of those probability assignments, of those probabilities. But you do know something about these probabilities. Presumably you know that they're normalized, and you may have constraints that tell you this is what we know about this probability, namely the expected value of some little f is some number f, capital F. So if this is what we know, we're going to maximize the entropy subject to these constraints. The result is a canonical distribution. It's a generalization of the Maxwell distributions, of the Boltzmann distributions, of the Gibbs distributions. This is a little bit more general here. So the probability of the alternative I involves a normalization constant that comes from something, a constant there that came from a Lagrange multiplier associated to this constraint here, multiplied by an exponential, and the exponential involves Lagrange multipliers associated to each one of the constraints of what we actually know about these probabilities. The dependence on I comes through these functions here that presumably have different values for different i's. Now, what are the Lagrange multipliers that appear in all of this? Well, the first one is just normalization. This probability distribution has to be normalized. And the second one, the Lagrange multipliers lambda, they're coming from the fact that whatever distribution you found, it has to satisfy this constraint. It has to give the right values for the expected values. The actual formula, as we saw last time, is this one that appears down here. So what we want to do today is extract some juice out of these expressions, analyze them a little bit further. So the first thing that we're going to do is compute what is the maximum entropy. So if this is the distribution that maximizes this entropy, what I'm going to do is I'm going to substitute this expression back here to calculate the maximum. The maximum entropy, the maximum value attained by the distribution is going to be, well, just substitute. And here I'm going to substitute, well, I'm going to be substituting there as well, but I'm going to substitute, let's see, let's go back here. I'm going to substitute this expression into the log back there in both these places. And so let's substitute. We have the log of z. It's going to be minus lambda k f k I. And I remind you that whenever indices appear repeated as they appear repeated here, k and k, right? They're being summed over. We're using the Einstein convention. So this is the log is going to be minus the log of z. And you can see here what's going on. When I want to compute the summation, pi fi, that's going to be, well, let's see, the minus and the minus give you a plus. Pi fi gives you the numerical value of the expected value. Now, this is also an indication of why it is that I didn't substitute the pi over here. It's because it's just going to give you the expected value that you know about. How about this guy here? You also get a minus and a minus, so this is a plus. And this is just a constant. So the sum over p's is 1. So here we get log of z. So this is the maximized value. Okay, before we proceed further, I would like to actually deal with one important issue here, and we want to get that out of the way. When we say we maximize the value of the entropy, and we find this value, the question that we want to ask is S max a local maximum or minimum, or is it just an inflection point? What is it? Or is it the global maximum? Maybe there are several maxima floating around. So when we say we found the maximum, did we? How do we not know it's not a minimum or something else, right? So the way to proceed this answer, the answer is actually, it is the global maximum. This is the maximum. There are no other maxima floating around. Answer S max is the global maximum. So how do we prove this? The way we prove this is we're going to consider all the probability distributions, consider the family of all the probability distributions that satisfy the same constraints. When I say the family of all, this is what we're going to mean by it's going to be the global maximum. Any other probability distribution that satisfies the constraints is going to have an entropy less than this maximum. Okay, so how do we prove that? Well, we use our old friend, the Kullback-Leibler, or the relative entropy. That's how we do it. Let's consider the following. We're going to compute the probability of any p prime relative to the p. And the way this goes is what we're going to have p prime log p prime divided by p. The first person who did this type of calculation involving this quantity was Gibbs himself. So this is where he came up with the Gibbs inequality. Remember, we proved this, that this is positive. So now I'm going to rewrite this log pi, just separate log pi prime divided by log pi, and get the minus log p, there is an I here, I'm sorry, get it onto the other side. log pi. Very good. At this point, if I were to flip the sign of these guys here, if I were to just multiply by -1, I multiply by -1 on both sides. When I do that, I have to invert the inequality. So the reason I'm doing this is that here on the left-hand side, it is clear that I have the entropy of those p primes that satisfy the same constraints. And this is going to be less or equal than the sum of the pi primes. Remind you what I'm just writing this out here, the sum of the pi primes, and here I'm going to write the log of pi. All right, what's the log of pi? If I go back here, the log of pi is minus this object exponent minus log z. So there is a minus sign and then the log of pi. So there is a minus sign and then the log of pi, which is minus lambda k f k I minus, that becomes a plus, log of z. And so this is less or equal than, there is the lambda k that I can bring out. And then I have the expected value of the little f with the p prime, which we know is fk. And we know it is the fk because the p primes are supposed to satisfy exactly the same constraints as the p. So that's the first term, lambda k, capital F. And then I have the last term. These guys are normalized. So this, the sum of these guys is 1. So we have plus log z. So our conclusion is that sp prime is less or equal to, but look at this expression here. It is exactly the same expression we had for S max. And we conclude that the entropy of any probability distribution that satisfies the same constraints as P is going to be less than the entropy of P, which is the entropy of the canonical distribution. Let's just write it like that. So this is the global maximum. It is the true maximum. When you maximize entropy subject to expected value constraints, you actually get the maximum. Very good. What can we do now? Notation. We have figured out that the maximum of the entropy, which is the entropy of the canonical distribution, and here I'm just going to write it once again. We figured out that the maximum of the entropy is given by this expression, and when the probability distribution is the canonical distribution. Now, from now on, we will drop the subscript maximum, and we're just gonna say, and this is nomenclature that comes from thermodynamics. So this is a nomenclature that's used by physicists. S max is called the entropy. Now the notation, the undenoted and denoted S. So now this notation is doubly confusing. First, we're going to call it the entropy, which may induce you to think that it's the only one. No, it's not the only one. There are many entropies. Remember the grouping property? To the same system, we could assign different entropies. You could assign a coarse grain entropy. You can assign a fine grain entropy. You could assign all sorts of things, right? So this is not the entropy. It happens to be the maximum of the entropy when the constraints are given by these Fs, right? Under those circumstances, of course, it is the only one. But you could have used different constraints. You could have done many different things. So to call it the entropy can be highly misleading. Remember, entropy is not a property of the system. It is a property of our description of the system. We could have different descriptions with different entropies. And to confuse the situation even further, we're just going to denote with the same letter S that we have been describing the entropy as a function of the probability distribution. It's the same letter. So what can I tell you? This is the way life is. People use language in ways that sometimes are conducive to confusion. Sometimes people call the latter the Shannon entropy, invented by Gibbs and Boltzmann. Sometimes people call this object the information entropy. That's all right. But the point I would like to make here is that there is only one entropy. We have made progress since the days of Clausius, right? So we will call the maximum the thermodynamic entropy, and we will call this guy the information entropy. But most of the time, we'll just call it entropy, and you are supposed to figure out from the context whether one is addressing the issue of what is the maximized entropy or what is the actual not maximized entropy. Entropy is a function of probability. So let us proceed. It's a matter of language, and so as with all languages, once you get used to the peculiarities of the subject, there is no source of confusion, provided you know that there are these two alternatives here. Let us proceed here. Notice here that Z. Let's proceed here. Let me. Z, the partition function, is the sum over all i's. This is just the normalization factor, right? And since I am summing over all i's, this object here, of course, does not depend on I. And these functions, little f's, are sort of like given. They could be, for example, the energy of the microstates or things like that. It's 1/2 mv squared. It's what it is. It's given, right? So Z is a function of the Lagrange multipliers. When we compute the maximized entropy here, how did we compute that maximized entropy? We computed the maximized entropy by requiring that the constraints be the capital F's. So the maximized entropy, which we're just going to write as S, happens to be a function of what those expected values are. So this is another way to be able to tell when we're using the letter S whether you're talking about the maximized entropy or not. If I tell you S is a function of the expected values, like entropy is a function of the energy, and maybe a function of the number of particles or things like that. If I tell you that S is a function of the energy, S is a function of the expected value, then you know it is the maximized value. If I tell you that S is a function of the probabilities, then you know it is the information entropy. The connection between the two, as we saw, is that S of F is lambda K Fk plus log Z of lambda. And this expression here that we've written it once, twice, we'll keep writing it, right? This expression here shows that the entropy is a Legendre transform S of F and log Z of lambda are Legendre transforms of each other. Let me elaborate a little bit on what this actually means. We're using F as being the constraints, and once we impose those constraints, we compute everything else, including the Lagrange multipliers. So the information that is conveyed by giving the capital F's, the constraints, is exactly the same information as being conveyed by giving the Lagrange multipliers. You can either give an expected value of the energy, or you can give the temperature. Same thing, right? We're going to come back to that later. So the information is exactly the same whether you have a description in terms of the partition function, or you have the same description in terms of S. And in fact, we did have that the derivative of log Z with respect to lambda is equal to minus Fk. You can compute from one, you can compute the other. Similarly, the derivative of S with respect to Fk is equal to, let's just compute it. Well, I'll give you the answer. This is going to be lambda K. We'll prove this. Proof. Here. Before I proceed, remember that I had mentioned that we have lower indices K and upper indices K in these expressions. And that there is a reason why this goes to the lower one and that one goes to the upper one. Well, you may recall from having studied either special relativity or general relativity or whatever relativity you studied, that if you differentiate with respect to a lower index, you're going to get an upper index, and vice versa. So the notation actually is extremely convenient in that it reflects this property. How do we do this derivative? Well, we just take this derivative here. We're going to take the derivative of S with respect to F K. Let me do the derivative. I want to take the derivative over here. I'm going to, in order to take the derivatives with respect to K, I would like to first change this index here to something else so that I don't confuse the index that I'm taking the derivative with respect to it and those indices there. So when I take the derivative of this with respect to f, first I have to figure out that, of course, if I change f, lambda is going to change. So I have to take the derivative of lambda with respect to fk and multiply by fl plus the derivative, I have the lambda l, the derivative of fl with respect to fk, that is going to be the derivative, the Kronecker delta, the derivative of fl with respect to fk, that of course is going to be 0 unless the L matches the k. That's exactly what I've written there. Plus the derivative of the last piece, we're going to take the derivative of log z with respect to lambda. I just noticed, fine, there is an extra step that I'm going to have to do there. The derivative of log z with respect to lambda, and I'm going to call it L, and then the derivative of lambda L, this goes downstairs, with respect to f. Okay, very good. Now notice what I have here. What I have there is this expression here, derivative of z with respect to Lagrange multiplier equals to minus fk. So this guy here is minus fl, which is exactly the opposite of what arises there. So this guy cancels out this guy. And what we're left with is just this expression here. So vs df k is equal to lambda k. What was to be proved? Quod erat demonstrandum, right? So let us just review what was going on here. When we have an expression of this form, we can show that the derivative of s with respect to f is the Lagrange multiplier, and the derivative of log z with respect to the Lagrange multiplier is the expected value. They're very symmetrical. That's what we mean by saying that these are Legendre transforms of each other. So these are basic expressions, basic formulas here. There is more juice that we can extract out of this. Very good. What is it we want to say? Yes. Now that we have a bunch of formulas, okay, before I proceed, if it starts seeming to you that the expressions that I'm writing down here are formally very, very similar to those that you obtain in statistical mechanics, that's exactly what they are. They're exactly the same formulas. Okay, so this was like the great discovery of Jaynes, when he started realizing that he could use the Shannon version of entropies, which provides a clear understanding of what an entropy is, and you could apply it to statistical mechanics. And the implications of this are absolutely enormous, because until Jaynes, people were thinking always that the laws of thermodynamics and the laws of statistical mechanics were laws of nature. While after Jaynes, what became clearer is that the laws of statistical mechanics and thermodynamics are not quite laws of nature, they are laws of inference or rules of inference or consequences of inference about nature. They are rules for processing information in the form of constraints about nature and from there drawing conclusions. So this uh, draws our attention to the fact that the laws of physics perhaps are not direct manifestations of what's going on out there in nature, but they're a hybrid. They are manifestations of what might be going out there in nature, but also of the processes of inference that we're carrying out with the very limited information that we happen to have. That is a major advance in our understanding what the laws of science actually are. It changes the way you look at science once you realize what's going on here. The contribution there happened very, very gradually, all the way from Maxwell, who realized that the second law was a matter of statistics, to Gibbs, that really cleaned up that notion a whole lot, to Shannon, in having discovered the versions of entropy in problems that have nothing to do with physics, in communication theory, to Jaynes finally bringing it all together and realizing that what you are doing when you're doing communication theory and what you're doing when you're doing statistical mechanics share the same formalism, the same mathematics, because you're dealing with problems that are similar. Not because the problems of physics are similar to those of communication theory. That's not the similarity. The similarity lies in that in both you have incomplete information and you're doing inference. The subject matter is completely different. One talking about atoms, in the other about communication channels. The subject matter is completely different. Very good. So let us proceed now. So now let us imagine what happens. What happens when we change the constraints? So suppose you have a constraint and you change it. So here we have the constraint. Remember what the constraint is. The constraint is the following. The probability involves certain functions, and you have several constraints, and you have these different numerical values. Now, in general, these functions here may depend on the particular variables at hand. I don't know, some x's, if this is going to be the energy of a microstate I, then the energy of the microstate may depend on positions, velocities, all sorts of weird things. Those are going to be the x's, right? It depends on I. What are the microstates? But the energies are also going to depend possibly on other things. Let's call the other things V. For example, if you have a particle in a box, like a potential, a box is a funny sort of potential, right? But if you have a particle in a potential, if you change the potential, you change the energy, right? You change the volume. This V, for example, so these guys that we're going to call them external parameters may include, for example, volume, external fields like electrical magnetic fields, and so on, right? So in addition to the actual microstates that we just described by I, there may be other parameters. And we may consider what happens when you change this delta V, this V. So let us figure out what happens when we change that. When we change the parameters or whatever, we do changes. A genetic change in the expected value is going to be something that comes from, let's just look it up here. A change in the expected value in the constraint may come from a change in the probability, or a change in the function f, because you change the v there, right? So it may come like that. A change in the function. So that's the kind of change that we have here. So whenever you're studying thermodynamics or any other process, you are interested in how things might change. Well, if you change the constraints, what happens? The constraint may change because either you change the probabilities or you change the functions f. Because these changes here are typically coming from changes into the external parameters, we may want to consider the quantity that is just the change when you change these guys here. That is what we're going to call a generalized form of work. Generalized work. If this change occurred because of change in a volume, whatever, you're going to have something like, for example, the generalized work is going to be pi, the change in this function with respect to the parameter v, and then the change in v. And whatever you have here, this you may end up calling, this is minus the pressure, right? The work is minus PVV if you have gases. If the volume changes because you squeeze it, the delta V is negative, you're doing positive work on the system. So this would be minus the pressure. If the V refers to a magnetic field, this object here would be called a magnetization, or a anyway, you can see that this is then what we say we have access to because you change parameters. Therefore, the remaining part which is, what is it? The remaining part is the other piece, pi delta pi fi k. This is what we're going to call generalized heat. The amazing thing about having these names is that, please notice, we're not necessarily doing physics here. You could be doing something in the stock market. So in this case, maybe you want to assign probabilities to stocks. And if you have certain pieces of information depending on F's, you can find out your canonical distributions. And then you can try to figure out what happens if you change external conditions, the V's, right? And so you can exert generalized work on the stock market, or you can figure out what is it that happens when you actually change in just the probabilities, and you might call that a generalized heat. So very good. Let's write this out a little bit more, and we're going to say, what is the change in the entropy now? The corresponding change in the entropy, in the maximized entropy, is going to come from the change in log z plus the change in the other piece for the entropy. We're going back to this expression back here. You want to figure out the change in S when you change the expected values. You're going to have those two pieces. Very good. So here we're going to have, this is going to be the change in log Z when you change, let's just write it out. This is going to be the change in log Z. Remember what Z is. It's the partition function. Let me write it here. Z is going to be the sum E minus lambda K Fki. So the change in log Z is going to be 1 over Z, and then the change in Z. What is the change in Z? The change in Z is going to come from changes in lambda and changes in F. So it's going to be the exponential. And then there's going to be the possible changes in lambda, F, plus the lambdas, the change in the F's. And all of this with a minus sign in front. So we have something like this. And then this becomes, if you were to put the Z under here, you see that that is just the probability. So what we have is minus delta lambda K, and it's the probability times the F's, Fk. And then for the second piece, what we have is the lambda K's. And we have again the probability multiplied by the delta F's. So we're going to have the expected value of delta F's, and all of this with a minus sign. So I got to fix this with a minus sign. So let me write the S now. The S is going to be minus delta lambda Fk. Minus the other piece there was that. My tablet is not reacting. Come on, wake up. Sometimes it does that, huh? Come on, there you go. Move there, yes. Minus lambda K delta F, lambda K delta, the expected value of delta F. And then there was the extra piece here, this guy here, delta lambda F minus delta lambda F minus lambda delta F. Now, let me just make sure that I got this right. I got the sign wrong. This is a plus sign here. So these guys are pluses, and this guy drops out. So the change in the entropy is going to be the lambda K, the last term. The change in the expected values minus lambda K the expected value of delta Fk. Now, if we go back to what the generalized heat was, this expression here, the generalized heat, but the generalized heat was delta pi Fki. And the generalized heat was written as the, let's just go back one more to this expression here. The change in F was the work and the heat. It's the delta F minus this guy here. So the generalized heat happens to be equal to the change in the F's minus the, what is it? The change in the F's. Let's go back to the expression and see it again. The heat. This there. This is that's the mistake I made here. Each one of these guys comes with a K, right? This is the generalized heat. It has a K there, generalized work. So I have to do the difference. The delta heat is delta Fk minus the work. So it's the change in F minus the change in the heat. So what we have here is precisely this stuff there. So delta S is equal to lambda K delta Q K. This may seem familiar if the F happens to be an energy, then the Lagrange multiplier is beta. It's 1 over T and 1 over KT, and so then the change in the entropy is going to be 1 over KT delta Q. So this is what leads you to the change in entropy is multiplied by T is equal to heat. An expression we're all familiar with, dq is TdS. Now, why does this K appear here? Well, it's because the distributions that the entropy that I'm considering here is minus P log P. I didn't put the K there, the Boltzmann constant. If I put it there, it disappears here. So what we consider as the thermodynamic entropy is minus K P log P. So that's the quantity that appears there. Very good. One last thing before we call for a break here. The one last thing is the following. Notice the following. The change in entropy has to do with the change in this generalized heat. What is the generalized heat? It's this expression that has to do with the probabilities. So you can immediately see here that if the probabilities do not change, there is no heat, and therefore the entropy does not change. So if the probabilities do not change, then the entropy, the heat, is 0 and the entropy change is 0. This is the analog in thermodynamics of saying that in an adiabatic process, the entropy does not change. In fact, it has to be a reversible adiabatic process, right? You're going from one situation of equilibrium to another. You're going from one situation of maximum entropy to another one. So that's the statement that appears there. Interesting. Once again, what we see here is that heat is something that is associated with the change of probabilities, while work is associated to the change in external parameters. Very good. Enough for now. I'll be back in a second.